Yeah, so good evening to everyone. My name is Jyotishwaran. I'm a student from PhD student from the EC department of the Indian Institute of Technology, Roorkee. Uh, Welcome to the weekly discussion session of the Physics of Nanoscale Devices NPTEL course. This will be our final session. So primarily we'll spend our time revising through the contents of the course, focusing on some important points, and for each topic that we are addressing, I shall do one or two example problems. So before we start, to the live attendees, do you guys have any questions, doubts?
Hello, sir.
Yeah.
Sir,
Hello.
actually, in the last week lecture, I saw the videos. In
Uh-huh.
that, I want to ask you about that. There are various functionals like GGA functionals and LDA functionals. So,
Yes.
is is there any separate importance for both? Like GGA provides some better accuracy compared to LDA, like that.
So it is essentially the difference is how they are framed. So rather than accuracy, the point there is what is the degree of complexity involved. Like I will let us go to that. So this would be like in the final lecture. Uh, yeah, can you give me just 1 second?
Yes, sir.
Yeah, yeah. So yeah, apologies for the interruption. So in this, yeah, let me just pop this out. And so yes. Uh, so where do we have like, did Sir cover LDA functions in this course? Yeah. Am I audible now?
Yes, sir.
Yeah. So there was some kind of a network issue before. Yeah. So what I was asking is like, were LDA functionals taught in your lectures? Kamal?
Sorry. Hello,
Yeah. Like you were asking about these
sir.
different like.
Actually, this
Ah,
discussion is on some exchange correlation, sir.
yes.
So, sir, actually, right now I'm using quantum etiquette. So, generally, we do some simulation so that we
Mm-hmm.
have to give some exchange correlation functionals. So, in that, we
Yes.
have various one, but in some maximum literature review, most of them using LDA and most of
Mm-hmm.
them using GGA functional. So,
Okay.
why they are preferring? Because maybe for bulk configuration some are using LDA-GGA and also for the device simulation they are using LDA-GGA. So
Okay.
that's why this
So
question comes into my mind while attending the lectures of that quantum etiquette,
uh-huh.
quantum dot devices in that lecture.
Yes. Yeah, so these things were not directly covered in the course. Yeah, that's what I was wondering. If these were
Yes,
like
sir.
covered in the course. Okay, you're asking with respect to your work. See, typically the different functionals that you use are, they come from like different approximations of the associated Hamiltonian. So,
Yes, sir.
like, if you are like basics of density functional theory is essentially that we take the wave function and we treat the multiparticle wave function as a density functional, and we substitute those in the various property equations, and there are associated equations and theorems for the behavior of the density functionals, and based on that we have different implementations. So given a problem, we start with the Hamiltonian, and so
Mhm.
the thing is I have not directly worked with density functional theory, but to the best of my understanding, uh, how it goes is like between these different formalisms, usually people take like different approaches to expressing the Hamiltonian. If there are some factorizations that can be done, if we can introduce some kind of additional operators into the picture, those things will lead to different density functional expansions. Now, which one is more accurate or less accurate? That thing, like one will have to look at the model and figure out like the accuracy of it. But the primary concern here would be
Understand, sir.
more about the computational complexity. Like people will usually prefer the model
Yes,
that can
sir.
be simulated more efficiently. So that would be a
Hmm.
bigger constraint, because even if you have a very accurate representation model, if the thing takes a lot of computational resources to run, then that is not very desirable.
Yes, sir.
Yeah, I know this
Okay,
is not
sir.
an exact
Thank you so
answer
much
to your
for the
question. Yeah.
information. No issue. And one thing I would like to
Hmm.
ask you that in that one word is like convergence.
Yes. Yeah.
So, sir, basically for the convergence, we have to iterate the various mathematical so that we can reach
Yes.
some tolerance.
Yes.
So, sir, if you correlate this thing into some application, then what is the meaning behind the convergence?
No, the convergence referred to here is a numerical process. So typically, when you're solving equations, especially when you're solving them using iterative methods, what essentially
Yes, sir.
happens is at different iterations, your solutions will be fluctuating. They will be moving, like they'll be varying in values for every iteration, the desired solution that you
Yes,
want to
sir.
get. Now, the idea is if this method were to be correct, at infinite iterations, this algorithm will have to give me a constant answer. That implies another assumption is after a given large number of steps, the degree to which the what to say like solution value after each iteration varies must also kind of reduce. So essentially, that is where we define this notion of tolerance. So typically, tolerances
Hmm.
might be defined around like some kind of a central value, or it might just be the gross differences, like the magnitude of difference between the solution from uh, one iteration to the next should be steadily decaying or reducing to the point where it goes below the tolerance. So that is kind of what we imply when we say that a given equation or an algorithm, like an equation solver or an algorithm, gives a convergent solution. So again, it's a purely computational term, at
Yeah,
least
understand, sir.
in this context.
Yes.
Yeah.
Okay, sir. So for today's motivation is that just to understand how to go for the final exam.
Yes, today the primary focus will be only that. So, however, if there are additional questions, I'll try to answer them, but I'd like to spend as much time as possible discussing doubts within the course. I want to highlight some important points and solve some associated questions. What I will mostly do is like I'll open your assignments again and pick up one or two problems from them and solve them step by step, going through the different what to say like steps for solving it, and also highlight which words to catch in a question and what kind of substitutions or formulae to use if you encounter a certain term in your examination. So yeah, that is that. So yeah, to the other attendees, any questions or queries before we move on? Okay, so there seem to be no questions. In that case, I shall begin like my part of the discussion. So, yeah. Uh, let's it. Title box can be removed. This. Just want to click and delete. Yes. Yeah. So, first things first, like important things to remember for the course, the basic idea, like motivation for our courses, we look at like nanoscale devices. So we are looking at devices with channel length.
Sir, are you sharing some PPT?
Oh, okay. Yeah, I have not shared the screen. I'm sorry. Yes. Apologies. Let me share the screen. Uh, yeah, I mean, I've been doing this for 12 weeks and even now it doesn't occur to me while I'm starting. I'm really sorry. Um, yes, you should be seeing it now. Yes, indeed. Yes. So generally, what we are looking at are devices with channel length of around 5 to 10, not 10, like around 5 to 20 nanometers. So if like channel length, let us say we are calling it L. If L is greater than 20 nanometers, then we have diffusive behavior. So if we have diffusive behavior, then this implies that one has to evaluate the transmission coefficient, T of E. And T of E is given by lambda of E divided by lambda of E plus L. So the smaller L becomes, the closer the transmission coefficient comes to 1. If your if L is less than or equal to 10 nanometers, you can assume that T of E is approximately equal to 1. You don't have to calculate this quantity time and time again. Is that clear?
Yes, sir.
So whenever you have a question where you've been, so let us look at the corresponding assignment questions. Uh, so let us go to week. Yeah, so I will, towards the end, I will come back to week 1, 2, and 3, the quantum mechanics and KP model and all of these things. I will come back in the end because summarizing that will be easier with respect to that. So we shall be beginning, yes, at around week 4, I suppose, or week 3, no, week 4. Even here, there are numerical questions, so I guess week 5 will have some of them. Yes. So, as you can see here, in this case, you've been asked, like, if the mean free path of the electrons in a conductor is equal to the length of the channel, then what the transmission coefficient would be. So, in this case, what we have to do is, I hope you guys know how to solve this question. But in any case, so if we are looking at, so what is this? Uh, this is assignment 5, question 7. So if we are looking at assignment 5, question 7, we have been told that lambda of E is we've been told that lambda of E is equal to L. So this implies T of E will be lambda of E divided by lambda of E plus L. So that will be L divided by L plus L. And therefore we have this is equal to 1 upon 2, and the answer is 0.5. So generally, you will see that in, I mean, you will have seen that in the assignment as well. Even in the exams, you will have questions that will test the extent to which you remember these relations and the context in where to use them, rather than give you raw numerical questions. Like, we'll not go, okay, if the mean free path is so many nanometers and the channel is so many nanometers, evaluate the transmission coefficient. Those kind of questions will not occur. So what you are supposed to do is look at what information is given and use the right kind of uh, right formula. So another thing that has to be remembered here is, so this is, yeah, first part. Now let me insert a new slide. View. Yeah. So yeah, so not T of E. Throughout the course, one of the primary equations that we have been using is, okay, I should not use this, 2q upon h integral t of e m of e times f1 minus f2 dE. So this is the current equation for a ballistic channel. Now, T of E is the transmission coefficient. This accounts for the diffusive behavior. And I've told you where and when to use this part. M of E is uh, the, so can anyone tell me what M of E represents? Like, what leads to the formation of modes? Anyone? Am I audible? Yeah, guys, can you hear me?
Yes, sir.
Yeah,
You
so
are audible.
I asked a question. Like, if you don't know the answer, you can tell me that you don't know the answer. That's fine. So, did you hear my question?
Yes, sir. You told how this mode comes into the current
Picture, like,
equation.
yeah, what role does modes play? What role do the modes play? Okay, so the modes correspond to the energy broadening. So energy broadening in turn, this depends on the finite transit time, and so this is the connection between because the electrons spend only a finite amount of time in the channel, in a ballistic channel, the energy levels are actually broadened in according to the Heisenberg uncertainty principle. So that is where we get this idea of modes from. In our previous week's discussions, you'd know that M of E for a 2D channel. So let me call it 2D is given by W divided by uh, lambda dB of E divided by 2. Let me write this correctly. Uh, so you can write this as the apologies, divided by lambda dB of E by 2. So this is where W is the width of the channel, 2D channel. So essentially, like we have a 2D channel that is like this with width W and length L, and electrons move along this direction. We are considering the conduction of electrons along this direction. So in terms of the picture of ballistic conduction, this is what we are looking at, and through all our derivations we find out that for a 2D channel the uh, number of modes is literally the number of half de Broglie. So lambda dB is the de Broglie wavelength, or the de Broglie wavelength. So this is the and the formula for this is h by p, where p is the momentum, or this is h by mv. So this is the notion of modes. And finally, we have for small bias voltages, we have the current equation that becomes 2q square upon, oh, not h bar, it's just h, correction, integral d of e m of e times. So for small voltages, and assuming that the source and drain materials are identical, this quantity will be replaced by the Fermi window function, dou f by dou ef. Like, I'm not going into the derivations because those things must have been covered in the course by now. So dB. So where V is the oh wait, no, I'm sorry, it's not dB. Apologies. For a small bias, yes, it will be dE times V. So this whole quantity takes in the form of the conductance So this is the conductance, and therefore the current is the conductance times the applied voltage bias. This is for small bias voltages V. Yes. Another thing, the last thing we have to remember for the ballistic conduction model is that for at T equal to 0 Kelvin, this function dou E by dou EF is actually equal to delta E minus EF. This is a Dirac delta function. And this is a property for any thing. So if I have an integral sum f of E into delta E minus EF dE, then this integral will directly be f of, let me not say f, I'm already using an f for the Fermi level. So let me say it is some function, what letter shall we use? Yeah, let me say it is some g of E. So this, we don't have to perform the integration when we have a Dirac delta function. The answer to this is g of EF. So these are the three important things to remember. Point one, like when to use the transmission coefficient. Point two is the idea of modes, and we have one more attendee.
Oh, Tekla. Hi, Tekla.
Yeah, yes, thank you. Uh, yes. So point two are all of these approximations, and we have the relationship between the de Broglie wavelength and the number of modes in a 2D channel. And the third point is this. Finally, given all of this, and let us say we have, okay, fine. So we have all this information. Now let us see how to solve a problem based on just the information that we have, what to say, like introduced over here. And we'll be using one more trick. So first we have a 2D channel. So now we come to the example problem. So this is the problem. Let me see if I can write this. That will make life easier. Uh, yes. So this is the problem that we are considering. So consider a 2D channel of length, say 25 nanometers and width of 15 nanometers. So the question is, what is the conductance of this channel at t equal to 0 Kelvin? So most of the cases where you have to evaluate this integral, at least insofar as the exam is concerned. Most of the cases where you have to evaluate this integral, you will be given that the temperature is 0 Kelvin. The reason why that is given is then this thing will become a Dirac delta function and you no longer have to perform the integration, because in general performing this integration is not trivial. So whenever you've been asked for the conductance, you will have seen in your assignment as well, we will be specifying that the temperature is 0 Kelvin. The reason we are specifying that is for you guys to remember this particular point. Now, in addition to this, we are also giving the surface charge density to be, say, 10 to the power 15 per centimeter square. So this is the question. Oh, yeah, should have actually put a question mark here. Yeah. So how do we solve this question? So before I start solving it quickly, just for the sake of curiosity, does anyone here have an idea how to solve this question? You don't have to tell the answer. You can just say yes or no, and then I will proceed to solve the question anyways. So do any of the live attendees know how to solve this question? How many of you don't know how to solve this question? Hello. Yeah. Uh, can you guys hear me? Kamal or Lakshmikanta, like, can you hear me? Am I audible?
Yes, sir.
Yeah. So you saw. Wait a second. Yeah, you saw the question, right?
Yes, sir.
So do you have an idea of how to solve it? Again, you don't have to tell me how to solve it. Just do you have an idea or no?
I know this. Maybe I maybe not.
Okay,
Here the
maybe.
formula will be that sheet charge. The density formula will be applied.
Yes. So that is the next relationship that we are going to use. Yeah, thank you for mentioning that. So in this case, the first thing that we are supposed to remember is at T equal to 0 Kelvin, the electrons will be occupied only up to, so how do we solve this? So the solution is as follows. So first we have to remember that at T equal to 0 Kelvin, all levels up to EF are filled and all levels above EF are empty. So this is the first thing that we are supposed to remember. Yeah, so what was I about to ask? So since you mentioned this, Lakshmikanta, can you tell me what the sheet charge formula is for the Fermi energy, or KF to be more precise? This is a 2D channel. Do you remember the formula? Have you like written it down somewhere, or should I just go ahead and do that as well? Okay, I'll do it either ways. But yeah, please remember to go back to your slides and revise these things. That is, the primary reason why I'm doing this. So yeah, so we have solution continued. So this implies that first and foremost, like since this is a 2D material, we know that the energy of the electron is given by uh, h bar square by 2m. Yeah, I'm assuming the effective mass of the electron is equal to the rest mass of the electron. So I'm not changing that. So we will have essentially kx squared plus ky squared. And we know that the highest uh, we know that the highest uh, sorry, so kx squared plus ky squared. So what I will do is the k space of this sorry the k space of this material is a 2D plane, so where we have kx and ky, and we know that at a radius of essentially what we will have is a very poorly drawn circle. Okay, this is getting atrocious. Give me just one more second. Yeah. Yes, this is slightly more tolerable. Yeah.
So it has been covered in our lectures.
Yeah, it has been covered. So can any of you tell me the formula? That's what I was asking.
Ns is equal to kf square by 2 pi.
Yes. Kf squared by 2 pi. And why is this?
Where kf is 2 effective mass ef by h bar square.
Yeah. Like that's what I've kind of written here. Like that's why I drew this figure. So how do we get this? Can you tell me? Because there might be questions regarding this for at least a 2D material. So essentially what we are looking at is the area for a single electron. In this space is given by 4 pi upon delta kf into delta ky. Sorry, why am I writing it as that? 4 pi into not delta kh into delta ky. It is the area for a single cell is delta kf into delta ky. That can be written in terms of Lx and Ly. We are not going to use that. So essentially, the entire area of this circle should contain ns many units. So that is the notion here. So why do we get a factor of 1 over 2 pi then? Shouldn't it just be pi kf squared? Any ideas?
Upspin, downspin.
Huh?
So there is an upspin and there is a downspin.
Well, that's technically not the reason. The reason is this. So this quantity is 2 pi into 2 pi divided by Lx into Ly. Correct? Like this quantity, like delta kf into delta ky is this quantity essentially. Like this you should remember from your basic quantum mechanics. So essentially what we will have is when we divide pi times kf squared divided by this quantity. So divided by 4 pi squared Yeah, and of course there is an upspin and a downspin, so there will be twice this. 4 pi squared divided by Lx Ly. This should be equal to the total number of electrons, not the concentration. So, like this Lx Ly will go to the numerator, that will come here, so that will give us the charge concentration, and the remaining quantity is this. So if you just move the variables around, you'll get this relation. So now, yeah. So that is where we get this quantity from. So okay, for the given value, what is kf? Can you tell me? Or rather, what is kf square? It is 2 pi into ns. And what is 2 pi into ns? It's 2 pi into, like for this formula, like for this problem. Like I've told you, ns is 10 to the power 15 per centimeter. So let us keep it at, SI units. So this will be 10 to the power 21 per meter squared. The reason I'm keeping it as kf square is because I want to find out what the Fermi energy is. Now that is h bar square upon 2m into kf squared. So we already know what kf squared is. Or rather, do we have to find? Actually, no. Yes. Yeah, so there is a trick we can use here. We don't even have to find what the Fermi energy is. So kf squared is this. Now another important thing to remember is the de Broglie wavelength is given by h by p, and we also know from quantum mechanics that p is equal to h bar times k. Therefore, the de Broglie wavelength is h divided by h bar k, that is equal to 2 pi divided by k. Is this clear? This implies the de Broglie wavelength is, in this case, so kf is square root of this quantity. So the de Broglie wavelength is, because here h bar is h by 2 pi, so the 2 pi goes up. So this is 2 pi divided by square root of 2 pi into 10 to the power 21, and the unit will be meters. Upon cancelling, this will be 2 pi divided by 10 to the power 21 meters. So this quantity comes out to be, let me quickly just calculate it. Have I done this correctly? Yeah, I think, okay, yes. I think I know what the mistake is. Let me just make one small modification here. Yeah, 10 to the power 15 is a bit too much for a 2D system. So things were like becoming slightly problematic. Oh, sorry. Yeah, so let us take ns to be 10 to the power 30. Then our problem will be more tractable. So in that case, yeah, everything will remain the same in the, oh, sorry, only this will change. So it will become 10 to the power 90. So again, over here, things will be 19 and 90. and yes. So this will come out to be something like 0.8 into 10 to the power minus 9 meters. So the de Broglie wavelength in this case is actually pretty small, even for 10 to the power 13, what to say, like electrons per centimeter squared. The oh wait, yeah, it's not. It's I have been making one very silly mistake. I've been multiplying it by a factor of 10 to the power 6. That should be done in the case of 3D materials. This is a 2D material, so I should only be doing by 10 to the power 4. So this is 10 to the power 17 per meter squared. Yeah. Apologies. Yes. So yeah, now it's correct. So now this comes out to be not 0.8 but 8 nanometers. So this approximately comes out to be 8 nanometers. So that is the de Broglie wavelength. So now that that is known, how do we calculate the conductance? Can anyone tell me now based on just what we have discussed? Anybody? Okay, I'll write it myself. So that implies M of E is equal to W divided by lambda dB at EF by 2. So this is 15 divided by 4 nanometers. So 15 divided by 4 is 7 divided by 2. So that is comes out to be 3.5. So another thing that needs to be remembered here is the number of modes is usually an integer. So, it's better to round it up. So in this case, we shall round it up to, since it's in the middle, yeah, we'll round it up to 4 modes. So the number of modes in this channel is 4. So since T equal to 0 Kelvin, we know that I is equal to 2q square upon h into T of EF into M of EF. Because this quantity becomes a Dirac delta function, this integral will vanish, and wherever I have E, we will just replace E by EF in accordance to this property here. So we have calculated M of EF to be 4. So we know this quantity is equal to 4. What should be the value of T of EF? Like, should we set this to be 1 or should this be calculated manually? So for that, we'll look at the
1,
yeah.
sir.
Huh? The length
1,
of the
sir.
channel is 25 nanometers.
Yes, because it's in nanometer scale.
Yeah, so, but it's still 25 nanometers. It is 3 times the mean free path.
Yes, sir.
Okay, like see, typically ballistic approximation should be taken when the channel length is at the mean free path or lesser than that. But in this case, this is 3 times, like well over 3 times. So we have to calculate T of EF. So that is equal to 8 divided by, so T of EF is equal to 8 divided by 8 into, so yeah, right now let us not do the approximation of 3.5 to 4. Let us just hold this. We'll take the complete approximation at the end. So 8 divided by plus 25. So that will give us a transmission coefficient of, so how much does this come out to be? This will be approximately 1 by 4 if I'm right. 8 divided by 33. Yeah, so this is approximately 1 by 4. Yes. So the transmission coefficient here is, yeah, this is 1 by 4. So yes, that implies, yeah, the total number of modes is now, like, including this, yeah, let me not write this approximation here. This is, so therefore, not I, yeah, I should have written G here. So G is equal to 2q squared upon H q squared upon H 1 by 4 into 15 by 4, like that is what this original quantity is. So this is equal to 2q squared upon H into 15 upon 16. Now we can say that this is approximately equal to, like, this quantity is approximately equal to 1, because the number of modes cannot be less than or equal to 1. So we will say that this is 1. So that you have to remember, that the number of modes cannot be a fraction. Number of modes literally means the number of channels that are available for the electrons to move from source to drain. So it is always going to be an integer value. It is going to be a whole number, not an integer value. It cannot be negative. So it has to be a whole number. So 15 by 16 is approximately 1, which implies at T equal to 0 Kelvin, the conductance of this channel is 2q square upon H. Is this clear? And do you guys know what this value is? You should know this by now. Anyone? Like, there have even been assignment questions regarding this. Does
1 by
anyone remember?
12.9.
1 by 12.9 what?
Kilo.
Just 12.9. Ha, yes.
Kilo.
So this is, yes, 1 by 12.9 into 10 to the power 3 ohms. Ohm. Okay. So again, as always for this problem, the value of ns and this I chose to be, like, relatively arbitrary. Like, I did not predetermine these values. I just fixed them as I was what to say, like, discussing the problem with you guys. So as you can see, doing the calculations, first we found out that the number of modes is actually 1. So this is typically what happens in devices. In a 2D channel device, like, this is also, like, slightly beyond the examination. The number of channels is not going to be very large. The number of channels is always going to be something like, you know, maybe 5 or 6 channels are going to be present. No more than that. And in the presence of the transmission coefficient, so now you also know what the effect of the transmission coefficient is. The transmission coefficient, due to the channel length, effectively reduces the number of modes. See, originally the number of modes was approximately equal to 4, but since the transmission coefficient is only 0.25, the effective number of modes became 1, and therefore the conductance became this value. So this is how we solve questions like this. Initially, very little information is given, like, you're just given the length of the channel, the width of the channel, and the number of electrons per unit centimeter, per unit area. Sometimes, instead of giving this, the total number of electrons might also be given. So pay attention to that. If the total number of electrons is given, then you know the length and the width, just divide by the area to get the surface carrier concentration. From that, we follow these steps to arrive at the final answer for the conductance of the channel. Of course, this answer is accurate only for small biases. Okay, at zero Kelvin for small biases. Okay, so this is how these kind of problems are solved. I hope that clears. So this is predominantly for problems that were discussed in weeks 5, 6, and 7, if I'm right. So the next thing I want to talk about is, yeah. So the next thing that I want to talk about is, let me go to the course page again. Yeah, please stop me in between and ask any questions that you guys might have. So even up to week 7, yeah, even up to week 7, we just have like the diffusive uh, transport and the notion of mobility and such. So yeah, as you can see, all the questions here are always given for T equal to 0 Kelvin. And you've been told like the Fermi level in this case has been explicitly mentioned. So using that, you can calculate the number of modes. And what other questions are here? So quick question. Do you guys know how to solve question 4 of this assignment? Does anyone have any doubts with this question? Like, I hope you can read the question. Or do you want me to like zoom into the page? Hello. Yeah, am I audible?
Yes, sir.
Yeah, so are people like familiar with the solution to this question here? We have a 2D channel where you've been asked to calculate the number of modes.
Yes, sir. It's a direct formula.
Yeah, so there is a direct formula for this. Okay, so yeah, and that's also one thing that you guys can be confident about. Most of the questions given to you, like given in the exam and in the assignment, will be using only direct formulae. You just have to remember which formula to pick up. Okay, so again, this notion of what to say, like diffusive mobility and the change of the apparent mobility. So, do you know how this changes with respect to a channel length? Like, are you guys familiar with the connection between the diffusive mobility and the apparent mobility?
Yes, sir.
Can you tell me what the formula is? Like,
It's like 1 by mu apparent is equal to 1 by mu diffusive plus 1 by mu
yes,
ballistic.
1 by mu ballistic. Yes. So essentially, if we were to treat like the whole thing in terms of mobility parameters, so yeah, let me switch to black again. So if we are looking at mobilities, 1 by mu, oh, one by mu apparent is equal to 1 by mu diffusive plus 1 by mu ballistic. So this is the relation. It's a harmonic mean. Similar relations will be appearing throughout the course for other reasons as well. So using this, we can solve essentially question, what is that, 7 or 8? Oh no, question 9 of assignment 7. So in this case, what we have to do is we'll have to calculate the diffusive mobility at 1 nanometer. So that will actually come out to be another 250, like given the mean free path is also 1 nanometer, like at what to say, like a channel length of 1 nanometer, we will have a transmission coefficient of half, and using that we can calculate that the diffusive, the ballistic mobility will also come out to be 250 centimeter square per volt second. So 1 upon 250 plus 1 upon 250 will give me 2 upon 250, which is 125 centimeter square per volt second. So that is how this question is solved. So these are the essential formulae you will need for solving conductance and modes
Hello,
related.
sir.
Yeah.
Sir, in this formula, 1 by mu
Yes.
apparent is equal to 1 by mu diffusive plus 1 by mu
Yes.
ballistic.
Yes.
So my simple question is that since we know that in a short channel device,
Yes.
nanometer scale, there is no scattering, where we are taking the transmission rate is 1. So previously in a bulk channel,
Yes.
this mobility concept was coming into picture due to scattering.
Yes.
But when we are going into ballistic, as we are taking that scattering, there is no scattering. Hence, why this mobility concept of ballistic is coming?
Okay, wonderful. Good question. So the point here is simple. What is the mean free path here? It is 1 nanometer. Like, is that clear?
Sir, yes, sir. Yes, sir.
So see, whether a given channel is ballistic or diffusive, it is with respect to the mean free path. So this is some hypothetical device. This is not a realistic device. Okay.
Yes,
so
sir.
in this hypothetical device, the mean free path itself is 1 nanometer. So for this device to have a channel where I neglect the scattering effects, I need to have a channel length of sub-nanometers, which is technically not possible. So this channel will show diffusive behavior no matter what the channel length is.
Yes, sir.
Yes. So like typically when we have short channel devices where the mean free path is larger, like see, let us go back to the previous example that we considered. I know the Debye wavelength is not a good approximation for the mean free path, but it is, a good estimate. So in this case, we know that the electron wavelength is around 8 nanometers. So if the channel length were 8 nanometers or less, then I can disregard all forms of scattering and I don't have to consider any diffusive mobility at all. The ballistic mobility is the apparent mobility. It is the total mobility of the electron. But in this case, we know that the channel length is thrice the de Broglie wavelength. And therefore, because of that, we have to kind of introduce the transmission coefficient. Is that clear?
Yes, sir.
So the same rule applies here. Like whether or not a channel is ballistic or diffusive, all depends on the mean free path that you are calculating. And how do we calculate the mean free path? We consider various situations. We look at what the parameters presented to us are. Like generally, we'll be given T equal to 0 Kelvin, or we'll be given some other conditions, and based on that, we will estimate what the typical length scale of the problem is. If the length scale itself is small, then both effects have to be considered. In this case, again, like we had to consider that. So the reason why we are using this formula, even for a channel that is ballistic, is that sometimes, like especially for this problem, like this device is not realistic at all. I mean, like it is impossible for an electron to have a mean free path of 1 nanometer. That implies that it is, literally getting scattered multiple times within the same atom. Like that physically is unimaginable. Like under normal circumstances, that thing is not going to happen. That will probably only happen in some kind of a nuclear reactor. So this is not occurring. However, if this is given to be the case, then you have to consider the diffusive mobility alongside the ballistic mobility. Okay.
Yes, sir. Got it, sir.
Yeah. All right. So let us move to the next set of topics that I wanted to talk about. Yeah, let me close this. So this is essentially weeks 5 through 7. I know I just discussed one problem, but in that one problem itself, like I've gone through how to calculate the modes, how to calculate the transmission coefficient, how to like consider the approximation of the Fermi window function, and what to say, like the special relation for the modes of a 2D channel, and the relationship between the surface charge density and the radius of the Fermi sphere. So for a 3D conductor, can you tell me what this relation will be? Like just out of curiosity. For a 3D channel, what will NS be? Sorry, not NS. What will N, the charge carrier concentration, will be? So we essentially have to use the same derivation as before. So what we will do is we will consider, yeah, I like. I hope this question does not appear in your. I mean, if it appears, well, good for you. No, I mean, forget what I said. So let me do this as a separate question itself. Let me come down here. Another problem. At t equal to 0 Kelvin. Oops. A 3D channel has a carrier concentration of n, per centimeter cube. Like so, essentially, or let me call it n naught. N equal to n naught. So the 3D channel has dimensions Lx, Ly, Lz, and the charge carrier concentration is n equal to n naught. So find Kf. So how we have to do this is essentially, in this case, the K space will be a three-dimensional space, and the isoenergy surface will be a sphere. So because of that, we have to consider the volume of the sphere. So we will have 4 pi by 3 kf cube divided by 2 into 4 pi by 3 times kf cube divided by the, again, the volume of an individual cell, that will be 2 pi cube divided by Lx, Ly, Lz. So this will be equal to the total number of charges present in the channel. So that will be n naught into Lx into Ly into Lz. So this and this will get cancelled. So because of that, this implies we will have what, 8 pi cube here and 8 pi up there. So I will have kf cube upon 3 pi cube, right? Yeah, everything else will get cancelled out. So 3 pi cube is equal to n naught, which implies kf is equal to pi into 3 n naught to the whole power 1 by 3. So this is the relation between the Fermi wave number and the what to say, like charge carrier concentration in the 3D channel. Now a question to the live to the attendees. Like I would like it if you guys can answer it. If the temperature were not equal to 0, will this derivation change? Anyone? Any of the attendees? Do you have any suggestions? Like now I showed you how to relate the surface charge concentration or the volume charge concentration to the Fermi sphere radius. What I'm asking is, and all of these derivations were done keeping the temperature to be 0 Kelvin. If the temperature were not 0 Kelvin, were to be higher than 0 Kelvin, will this derivation still hold? So yes or no question. Can somebody take a guess?
I think, sir, no.
Why?
As
See, the only question you are supposed to ask yourself at this point is, does the Fermi level change with temperature?
yes, yes.
Does it? Does the Fermi energy change with temperature?
Oh, Fermi energy.
Yeah.
Achha. Okay, okay.
Does it change?
No, sir.
Yeah. So with that, let's jump to, now let us take a step back. Yeah, so this is the reason why I did not do the quantum mechanics part. Now we shall, of course, do that. So, yes. So again, for the topics in quantum mechanics, I'm going to move in the backwards order. So we shall look at the Fermi statistics or the Fermi-Dirac statistics. So f of e, oh, apologies. F of e is equal to 1 upon 1 plus exponential e minus ef, sorry, I was in a hurry and I wrote ek, e minus ef upon kbt. So over here, this quantity ef does not change with temperature. So kf is directly related to ef. So even at non-zero temperatures, this particular derivation is not inaccurate. The only thing that will change is in non-zero temperatures, this relation will no longer hold. Okay, so this derivation for connecting the Fermi wavelength, or rather the Fermi wave number, to the total charge carrier concentration is valid at all temperatures. So even when T is not equal to 0, don't be afraid to use either this formula or this formula for a 2D and a 3D channel respectively. Okay, and you can also do a similar derivation for a 1D channel as well, but I'm leaving that out. Okay, so essentially what this means is, at T equal to 0 Kelvin, we have distribution like this, and this is E equal to EF. At higher temperatures, we'll essentially have this quantity kind of like going this way and like, and at this point, the value of the function is half. So this is 0 and this is 1. F of E is on the y-axis and E is on the x-axis. So this is, and no matter how much we increase the temperature, even at higher temperatures, again, this will like become okay. So at higher temperatures, this might even like fall from this value, and it might go like this and like this. But no matter what happens, at every temperature, the Fermi Dirac function at E equal to EF will have the same value half, and this EF will not vary. Okay, so EF does not vary with temperature. Please remember this. The only thing that can make EF vary is the total number of electrons. So if I introduce more electrons or more fermions into this system, then the EF will shift. Or if I'm applying some kind of an external potential and changing the energy level itself, then EF will shift. These are the only two cases when the Fermi level will change. When an external potential will, like EF will change only when electron concentration changes or external voltage is applied. Okay. So this is the Fermi Dirac function. Of course, integral 0 to infinity of f of e dE is what? Can anyone tell me what the value of this integral is? Okay, so this is essentially the total probability. So this integral will always be equal to 1. Remember this. And then we have the Fermi window functions. So we have the Fermi window functions. As mentioned before, the Fermi window functions can be written as dou f upon dou E, which is equal to minus dou f upon dou EF. So this is a useful substitution that can be done in different situations. Of course, this quantity can be explicitly evaluated over here. So it will come out to be minus 1 over the square of this quantity. You know what? Why am I wasting time on this? This part has been done in the lecture, so please go and revise these things. Now taking a further step back because we have only like 30 to 40 minutes left. So yeah, let me jump ahead to basics of quantum mechanics. So insofar as quantum mechanics is concerned, the important parts are particle in a box. Again, since this is an objective only examination, no derivations are required. Just remember this, En is equal to n squared, pi squared, h squared, h bar squared, sorry, upon 2n or n star L squared, where n where n is equal to 1, 2, 3, and so on. Okay, and we also have the chronic penny model. Of course, the derivation for this is extensive, but the important things to remember in the chronic penny model are as follows. So, what is the first thing we get from the chronic penny model? The first thing we get is the band structure in a periodic potential, and from the notion of bands, we can arrive at the concept of Brillouin zones. So, for a 1D material, the chronic penny model is for a 1D solid only. The first Brillouin zone, the first Brillouin zone goes from minus pi by. So let us assume that the potential for the KP model kind of like, let me assume that this complete period that repeats itself, let me assume this complete length is L. Okay, I'm not identifying them as A and B. So this is B and this is X. So yeah, the potential is kind of repeating itself periodically. So this length is L. So the first Brillouin zone will lie between minus pi by L to plus pi by L. The second Brillouin zone will lie from minus 2 pi by L to pi by L. Pi by L to 2 pi by L. And so on. So essentially what happens is, like when we have the different Brillouin zones, like only the first Brillouin zone will be a continuous region. Like if we are looking at the K space, the first Brillouin zone will be between this. So this is my first Brillouin zone, whereas the second Brillouin zone will be this part and this part. Like it will be a union of these two. Similarly, the third Brillouin zone will be the union of those two chunks. And of course, in the reduced band structure, the reduced model, like kind of this point, the EK relationship graph from this point is brought into this point, and the region over here is brought into the right half of this, and similarly such transpositions take place. So remember that for any nth Brillouin zone, this is how the K values will be split. So this is for the KP model. What else is there in this case? And again, like there will not be very many numerical questions in this. You will just have to remember what the what is it, like zone boundaries, where the zone boundaries are. And so as you can see, like if you are looking at like, sorry, let me go to the assignments for week 2. No. Yes. So yeah, as you can see, all of the questions here are only qualitative. And yeah, kind of remember this graph and its properties as to how to identify the transcendental equation and things like that. Go back and read why this graph is used, and you know what the significance of these shaded regions are, and how the sizes of the various bands will change as we are moving to higher Brillouin zones. So learn about those properties as well. And yeah, one more, I mean, the last thing for the basics is the effective mass. So the effective mass in general is so the effective mass is given by yeah, can someone tell me what the formula for the effective mass is? At least at the bottom of the conduction band.
Yeah, you can find this by the formula energy is equal to h square k square by 2 m star.
Yes. Okay.
From that m star we can find out.
No. Like what I'm asking is, I'm asking the effective mass in terms of the EK diagram.
Then it will depend on inversely proportional to the curvature
So
of
what
the
is the
EK
relation there?
parabola. D square E by dk square or something like that.
Yes. So it will be h bar square into d squared E upon dk squared whole bar minus 1. Is that clear?
Yes, sir.
Okay. Now, because of this, in the KP model, what will happen to the effective mass at the middle of a band? Essentially, now let me consider in the reduced picture. So we have our first, like our first, let me be slightly more accurate. Our first Brillouin zone will lead to a band formation like this. So it will be something like this. And the second band will be like this, and so on and so forth. So we will have different bands going up. What I'm asking is, what will happen somewhere in the middle of this Brillouin zone? What will be the effective mass? Just look at this formula and give me a guess. Okay, what is the value of the effective mass as the minimum? Huh?
Are you asking is it negative or positive or it is?
No, I'm asking. Yes, you can also tell it that term. Like what will happen in the middle of the band? Yeah, you're taking the right approach.
Okay, sir.
Okay, so at the band minimum, what is the sign of the second derivative? I mean, this is a calculus. So for a minima criteria, the second derivative has to be negative.
Yes, sir.
Okay, so this is the band minimum. Therefore, at this point, we will have m star is negative.
Negative, sir.
At this point, we will have m star is positive because this
Positive.
is the maxima. So if the second derivative is going from negative to positive, somewhere in between, the second derivative will become 0. Is that clear?
Yes, sir.
The second derivative is negative at this point, it is positive at this point. So somewhere in the middle, it is going to go to 0. The second derivative will become 0. At that point, the effective mass is actually infinite. Okay, so remember that. In the middle of the band, of any band, the effective masses will be very high. Theoretically, it will be infinity. That is why we say only the electrons near the edge of the bands, either at the band maximum or the band minimum, either the valence band maximum or the conduction band minimum take part in conduction. Because somewhere in the middle, the effective mass is infinity. So no matter what kind of a potential I will apply, the electron will not respond to that potential. Is that clear?
So yes, sir.
Okay, so somewhere in the middle, m star is infinity. there might be a question that asks you to evaluate the effective mass at some point in the middle. You might be given a KP, some kind of an EK relation, and you might be asked to find what the effective mass at a certain point is. So use this formula, calculate d square A upon dk squared, substitute the value of k, and get the answer. So this is like the basics of quantum mechanics along with the properties of the Fermi function. So this part is also done. Yeah. One more thing I want to tell you is I cannot do any numericals for this. So I will just directly go to the lectures themselves. So where is that? Oh, I think it is week 6. Yes. So these things are important. However, there are going to be no numericals based on this. But remember that, yeah, so as you can see here, at t equal to 0 Kelvin, for a purely ballistic channel, you just have to multiply the quantum of conductance into the number of modes. That is it. And the number of modes for different things, we have different formulae for that. And again, it is convenient to relate this thing to the 2D charge carrier density, so the formula here is given. But the thing I wanted to talk about is this, the Fermi-Dirac integrals. So for different such expressions, different Fermi-Dirac integrals, Fermi-Dirac integrals of different orders will be used. You will not be asked to evaluate the Fermi-Dirac integrals, that part is not in the syllabus. Nobody is going to ask you that. But you have to remember what Fermi-Dirac integrals appear. That is something you will have to learn by heart. There will definitely be questions based on that. Okay, why is this not loading? Yes. Yeah. So as you can see, for different, for the charge carrier density for a 2D material, you'll have Fermi-Dirac integral of order 0. For a 1D material, you might have Fermi-Dirac integral of order -half. For a 2D integral, you might have a different order of Fermi-Dirac integral. The point is, you will have to remember these things manually, and there is no way of getting around it. How to remember that and how to infer that, I've discussed in one of the previous week's sessions. Probably week 8 or 9, no, probably week 7 or 8. So you can go back and see those videos also. That should kind of tell you how to find out what Fermi-Dirac integrals appear where. So a good chunk of questions might be based on only this. Also learn some of the properties of the Fermi-Dirac integrals. So that is another piece of advice I wanted to give you guys. Yeah, now we are moving to the latter part of the course, weeks 8 through 12. Week 12, as far as the numericals are concerned, so quick question. You guys have done all the assignments. So how did you find assignment 12 to be? Were you able to solve the questions correctly? Did you have any difficulties with the questions? Were you able to solve question 7?
No, sir. It was a little bit tricky, I think so.
Okay, fine. So let me discuss question 7. Okay, so yeah, again, over here also I will kind of move backwards. Eventually I will talk about the MOSFET properties. Yeah, so question 7 here. what is asked is, there is an artificial atom at t equal to 0 with energy levels given by minus 50 upon n square, where n are these values 1, 2, 3 and so on. Each level can hold up to 2 electrons, and what has been asked is the difference between the ionization potential and the electron affinity when the system contains 8 electrons. Okay, so how to do this? Essentially what is given here is, oh sorry, what is given here is the following. Like we know that En is equal to, oh, let me change the color and quickly solve. So this is assignment 12, question what? Question 7, yes. Yes, assignment 12, question 7. So we know that En is minus 50 upon n squared. Oh, sorry. Now the negative sign just implies that the electrons are bound. Okay. And also that as n increases, the energy values also kind of go up. So what is happening is, the energy levels are kind of like this. Initially it is minus 50. After that it is minus 50 by 4. So that will come out to be minus 12.5. And after that the difference should kind of become closer if I'm right. So by 9, so that will be minus 5 point something, right? Yeah, it will be minus 5.56 or something like that. Yeah, yes, it will be minus 5.56. So that is minus 50 by 9. So yeah, let me just draw this graph properly. Why is it not? What's happening here? It's writing, but somehow it's not. Okay. Why am I unable to erase this? Yes, good. Yeah. So we have the energy levels that go as minus 50, and then we have a relatively bigger jump to minus 12.5, and then we have a slightly smaller jump to minus 5.6, and then further above it will be 50 by 16 and so on and so forth. So the thing that we are supposed to remember here is that this system has 8 electrons. So if it has 8 electrons, how many levels are occupied? 8 electrons are present. Then up to n equal to 4 is occupied. Is that clear? Because each level can contain only 2 electrons. So n equal to 1 will contain 2 electrons here. N equal to 2 will contain 2 electrons here. N equal to 3 will contain 2 electrons here. And similarly somewhere above here, like 50 by 16 will come to like minus 3 point, minus 3.0625 or something like that. So it should be minus 3.06. So we will have like these levels filled. So n equal to 5, that will correspond to minus 2. So E5 is the first unoccupied level. So that is minus 50 by 25. That is equal to minus 2 electron volts. I think the unit of energy is given to be electron volts, right? Yes, electron volts. So this is the energy of the highest, or rather the lowest unoccupied, molecular orbital. So this is the LUMO, and this is the highest occupied molecular orbital. So this is the HOMO. This is the LUMO and this is the HOMO. Now, what is the ionization potential? So what is the ionization potential for this system? What is the IP for this system? Can anyone tell me? Do you know how to find the ionization potential? Hello? Yeah, can you guys hear me?
Yes, sir.
So difference between LUMO and HOMO?
Huh?
Difference between LUMO and HOMO?
Okay, that is the final answer, yes, but the ionization potential is not difference between LUMO and HOMO. The ionization potential is the difference between the HOMO and the vacuum energy. And in this
Vacuum energy,
case, yes. So in this case, the vacuum energy is n tends to infinity. As n tends to infinity, we know that E tends to 0. Therefore, this is E HOMO minus E vacuum. And we know E vacuum is 0. So this is, or rather it is E vacuum minus E HOMO. I'm sorry. Like that is how that is the correct way to write it, because the vacuum energy is the higher energy level. So it is always written as higher minus lower. So it should be written as E vac minus E HOMO. So in this case, this will come out to be minus E HOMO. Therefore, that is minus 50 by 4 squared. Okay. So whatever that value is, I'm not calculating it. Now the electron affinity is the energy required to introduce one new electron. So that will be E vacuum. So that is 0 over here. This is E vac. That will be that minus E5, the LUMO energy. So the electron affinity EA will be equal to 50 divided by 5 square. Therefore, IP minus EA, the difference between the ionization potential and the electron affinity, like here we are looking at the modulus of this quantity, will be 50 into 1 by 4 squared minus 1 by 5 squared. So this quantity will come out to be, what will this come out to be? This will be 25 minus 16 divided by 400. So that is 400? Yes, 400. 25 into 16. So that will be 9. So 50 into 9 divided by 400. That is equal to 450 by 400. And that is what? 4 by 4.5. 4.5 by 4. That will come to 1.125. And is that the correct answer? Yeah, I think that is the correct answer. So yeah, the answer is 1.125 electron volts. Is it clear now?
Yes, sir.
Okay, so like go back to your slides, and this part I've also discussed in detail in last week's video also. Like whenever you're looking at quantum dot based devices, the important things to remember are the HOMO energy level, the LUMO energy level, and the vacuum energy level. So these are the relevant quantities. Like if you know these things, then all of these questions can be intuitively answered. Again, there will not be any numerical questions relating to the thermoelectric effect other than like some very elementary calculation of coefficients. But there will be qualitative questions like this. So, like essentially you've been asked to calculate what the thermoelectric conductance, the Sore coefficient at near zero temperatures is. So in this case, what you will find out is that dou F upon dou E at near zero temperatures, the Fermi function becomes flat. Okay, so since the Fermi function becomes flat, like if we can go back to the thermoelectric effects slide. Yes. So the where is ST? Yes, we have it here. So and the connection between ST and delta T is this. Yes. So see, ST is this times G of E. Now at T equal to, and G of E for small bias voltages has this Fermi derivative function. Now at T equal to 0 Kelvin, the Fermi function will be nearly a constant. Since that is nearly a constant, the derivative will be 0. Dou F naught by dou E will be 0. Since this quantity becomes nearly 0, this entire relationship will also become 0. So because of that, in this question, like essentially that is the fact that you were supposed to remember in, in this question over here. In case anybody had any difficulties, over here the correct answer is 0. So the reason for that is at near zero lattice temperatures, as I have mentioned previously here. Okay, yeah, I forgot to mention that this is T equal to 0 Kelvin. So this is T equal to 0 Kelvin. So at T equal to 0 Kelvin, this line is flat. Therefore, the derivative with respect to energy of this function will be 0. And since that is the factor that appears in the Sorey coefficient and the conductance, at near 0 temperatures, the thermoelectric conductance becomes 0 for a material. Okay, so that bit is done. Yeah, so finally, let me go back to mass electrostatics. Go through the slides and read the important, concepts. However, insofar as numericals go, the most important part that you guys have to remember are these three formulae. These three formulae, like the formulae in these two slides, is essentially what you have to remember to solve most of the problems for mass electrostatics. Is that clear? Like for the numerical problems that you will encounter, I'm sure when you solve the assignment also you might have noticed this. The only things that you have to use are essentially the depletion layer width, the surface potential, and the corresponding relationship between the inversion layer thickness and the depletion width. Before last week, the week 10 session contains an illustration, a numerical illustration for this bit. I have done it in that, so please go back and refer to that. So that is what you have to, like, these two slides will contain all the essential information. You need to solve numerical questions. I'm not saying please don't read everything else. Read these to solve the numericals. Read beyond this, like for answering the theory related questions. And remember that in your final exam, you will actually have more theory based questions than numerical questions. So remember the conceptual discussions that we have had over the weeks. That is why I spent the first 10 weeks, you might have noticed. Let me stop presenting for a second. You might have noticed that in my, if you've seen my previous week videos, I actually solve very few problems. Rather than solving problems, I keep discussing concepts over and over again, like even going so far as to repeat the contents of the lectures. The reason for that is to kind of emphasize on important concepts that will appear in questions. So when you go and give your examination, you will find that around maybe 33%, like 1/3 of the questions are going to be numerical and the rest will be conceptual. So for the numerical parts, I've told you almost all the tricks that are necessary. When t equal to 0, you don't have to perform any integrals, like everything will reduce to the Fermi energy values. How to relate the Fermi energy to the charge carrier concentration is also known. Most of the questions that will be asked will be for 2D channels. Occasionally there may be 1D channel questions. Remember that. And oh yes, I hope I don't have to mention this to you, but finally, last but by no means the least, and do not forget this, please do not mess it up. If there is one thing you guys are remembering from this entire course, let it be this. It is, yeah, I mean, this is as good a note as any to finish. The dependence of the density of state on energies. Please do not mix this up. It is proportional to e to the power minus half, e to the power 0, and e to the power half. In what cases? Can someone tell me quickly?
Sir, it's all about 2D, 3D, and 1D.
So it's 2D, 3D, and 1D.
Yes, matlab,
Is that the order? Do you want me
no,
to write
no,
2D,
no,
3D?
no, 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 no. In 2D, it is root over.
Are you sure? So this is 2D.
No, sir. Actually,
This is 2D.
It is a bit rusty.
Yeah, I know. Like that is why. Please go back and revise this. In any event, I'm telling you right now. This is 1D, this is 2D, and this is 3D. Okay. This is the density of states. G of E is the density of states. Do not forget this. Like this is one of the first derivations that was done. An entire week was dedicated to this very concept, and this is important. So for a 1D channel, density of states is proportional to e to the power minus half. For a 2D channel, it's independent of the energy. For a 3D channel, it is proportional to square root of energy. Modes, e to the power 0 for a 1D channel, e to the power half for a 2D channel, and e to the power 1 essentially for a 3D channel. Okay, so these are the relations. Do not forget them. Please do not mess it up. And like that is the thing in this course, insofar as the exam is concerned, there is wait, have I been? Yeah, I have not shared my screen, but no worries, the slides will be visible in the video. Yeah, so as you can, yeah, so as you can see, where M of E is the moles. Okay, so this is the energy dependence. Of course, at t equal to 0, none of these dependencies matter. You are just like evaluating a function. But just remember these dependencies. Please don't mix them up. Remembering these dependencies will also help you remember what kind of Fermi-Dirac integrals appear in various expressions. Okay, so go back and see the video for week 6 or 7 or maybe 7 or 8. In that, I have gone through the same things again, and I have mentioned how to identify what kind of Fermi-Dirac integrals will appear for the various like quantities that we shall be discussing. Okay. Yes. So, yeah. These are kind of the things I wanted to tell you guys. Like again, in a 2-hour session, it is impossible to cover everything that is in the course. But I just wanted to touch upon like 1 or 2 important things that if you guys remember, you should be able to deal with the exam relatively easily. So, insofar as the numericals are concerned, these are the parts. Of course, these slides and this lecture will be shared immediately. I will not delay this time because your exams are approaching. So, as soon as this session is over, I shall be uploading this video. Uh, yeah, I think with this, I am done on my part. However, I'd like to ask you guys if you have any like last minute questions that you'd like to ask. However, yeah, beyond this, if you still have any questions, please post them on the forums. I do visit the forum regularly. So if you still have any further questions, please ask them there. I will be more than eager to answer them. There are also other TAs who will answer those questions. But yeah, before we conclude this session, does anyone have any questions or queries?
No, sir.
No. Okay, good. All right. So in that case, I think I can conclude the session now.
Sir.
So yeah.
But while going through this course,
Yes.
in my personal opinion, I found it quite interesting, and I think that this is just a tip of the iceberg.
Yes.
And there are many things is discovered, and there are many things yet to be discovered.
Yes.
So while in our UG and PG course, while reading about bulk semiconductors, I always wondered that what is next. What is next? This concept was quite puzzling me for quite some time, and while going through this course, I found out that yes, actually these are the physics related to this, and when we are increasing the channel length, what are the odds coming into the pictures? Like
Yes.
today channel length is 10 nanometer, tomorrow it will be some few nanometer, so there will be quantum dot. And somewhere in the lectures professor also taught about that maybe angstrom level can come also. I
Yes.
don't know. So it was quite interesting, and I sincerely thanks all professors and TA for introducing this course.
Of
And
course. Yeah.
thank you, sir.
Yeah, it has been, I mean, our pleasure, our collective pleasure. I can even speak to a certain extent for the instructor, as I am his student as well. Yeah, so you guys are all welcome, and it has been my pleasure interacting with you guys over the last few months. Uh, so yeah, as Lakshmikanta mentioned, this course is an introductory course. Like we are not going too much into the technical details of the field because that is pretty vast, and to cover it in a single 12-week contact course is kind of impossible. However, we wanted to cover the basic, like as the course title suggests, this is the physics of nanoscale devices. So we wanted to give the basic tools which people can use to analyze these devices at different contexts. So that is why you were taught ballistic conductance, like the Landover model of conductance, or how to extend that to do to the electrostatics, or subsequently, like of course in the last couple of lectures, people even spoke about things like density functional theory and stuff like that, which is required for the analysis of quantum dot devices. So essentially the aim is to introduce the techniques and give you some kind of a physical background. So the main thrust of the questions and the examinations in this course will also be towards the again, the techniques and the physical background rather than numerical. So this is not going to be a case where you will have to solve problem after problem after problem in the exams. The questions will be more conceptual. So spend the time that you have focusing more on the concepts, and even the numericals that you will have, you will notice that at most the amount of calculation that you will have to do is maybe do a couple of divisions and take a square root. So you will not need more numerical power than that. Like beyond that, the questions will not be any more complicated. At best, you will have to add or subtract. Worst, you will have to do some multiplication division, and you have to take the odd square root, and that is that. So don't fret too much about the numericals. focus more on the concepts and focus more on the reason why things are being done. In today's session, I have not spoken much about strain engineering. Last week, I spent a good amount of time talking about strain engineering and the impact of strain on device performance. You guys can, alongside of the lectures, you can also refer to last week's discussions for that. That might also help you in approaching and addressing some of the questions. So yes, with that, I think I can conclude today's session. Once again, I thank you all for attending over the past few weeks. Like when this session initially began, I was not sure even if one person would be willing to show up. But yeah, there has been a consistent attendance through and through, and I've received a reasonable amount of feedback through my interactions with you guys. I thank you personally for that. It has been a good experience for me, and by covering these topics for you guys, I have a feeling that now I understand the contents of this course significantly better. So in that way, you guys have helped me enormously. Uh, so that is that. I wish you all the best for your examinations and all your future endeavors. So with that, I'm ending this session. All the best. Bye.
Thank you, sir. Sir, is there any way to contact you, or the forum is the only way?
You should be able to find my email ID should be available somewhere on the documents. Like in the TA details or something, my email ID should be present. If it's not
Yes,
present,
sir.
it should be there. So you can contact me on my email.
Okay, sir.
Okay, like I mean that is my regular institute email ID. So you can write an email to me anytime, and I'll be more than happy to respond to any inquiries or anything that you have to say. All right.
Thank you, sir. Thank you, sir.
Okay. Yes.